We said the thermal conductivity, we're dealing with gold, so let's put that in. Delta X, delta Y, 0.05. And Q dot, there's no internal generation. And it would be a case where we have this type of boundary where we have insulation on the left. So I'm going to do a copy, and then I'm going to go back up, and I will paste in all of these cells. And there we go. And now the bottom one, I'm going to look for the corner. So let's look for insulation in a bottom corner. Yeah, so what we're going to do, we're going to assume there's insulation on the bottom. We know there really isn't because that's the constant heat flux boundary. But I haven't gone through and come up with insulated on the left and constant heat flux on the bottom. If you're so inclined, you could come up with all those boundary conditions, but I did not do that when I created the spreadsheet. And what I'm going to do, I'm going to paste that one in. And now what we need to do, let's handle these ones. These are constant heat flux from the bottom. So we scroll down in the spreadsheet looking for constant heat flux. It's not insulated. Constant heat flux with convection. No, we don't have convection in this case. Constant heat flux boundary. There we go. And what was the value? We were told it was 100 watts per square meter, so I'll enter 100 there. We said that we were dealing with a gold plate, so 317.05 for delta X, delta Y. There is no internal generation, and so I leave that blank. And now we look for the appropriate boundary condition. It's this one right here, because we have the bottom surface with constant heat flux. So I click there, I do Control C, and then I go up. There we go, there's our spreadsheet. I drag across and I do Control V to paste in the value for the boundary condition. It's interesting, went to 25.01, not really sure why. Close to 25, there must be some sort of anomaly. Let me see here. If I click there, what is it pulling in? It's pulling in those values. So I'm not sure what would be driving that. It could be round off errors somewhere in the spreadsheet. Not a big deal, it's close to 25. And the last thing we need to do, now that we've done all of this, we copy and paste the internal cells. So what we do, we click on the interior node, and if we look at the formula bar, we see the interior node is being represented by all of the adjoining ones. So we click on that, we'll do Control C, and then I'm going to copy, and I'll select and then do Control V. And there we go. Look at that. Heat transfer taking place before our eyes. And so what this is going to do, it's going to work, trying to converge. I will keep pushing F9. So there we go, we're getting to convergence, and that's a pretty boring looking solution. The temperature going from 25.29 at the bottom to 25.23 at the top. And I wonder if this is not because we've used such a high thermal conductivity. So let's give something a try here. What I'm going to do, I'm going to drop the thermal conductivity in all of the boundary conditions that we've assigned. Let's drop it down to 100. So we'll change that, and then let's look for all the other ones. There's one, 100. Maybe that's why heat transfer textbooks rarely use gold. There's heat flux was 100 watts per square meter. We'll put 100 there. And let's see, were there any other boundaries that we used? No, I think those were all of them. We didn't use radiation. Okay, so let's go back up to our grid. And I'm going to hit F9 again, and we'll see where that takes us by changing the thermal conductivity of the plate. Again, that's pretty boring. Not much going on. Let's try reducing the convective heat transfer coefficient. So let's drop that to more of a natural convective heat transfer. Let's try 10. I see a lot of stuff going on there, but were there any other places where we had to enter the convective heat transfer coefficient? Insulated boundary, no, that just had thermal conductivity. That one, surface heat flux, no, we had nothing with the... Okay, so I think that was the only one. Let me go back up. So we've dropped the convective heat transfer coefficient now, and I'll keep pushing F9 to see what we get on convergence. So this is taking quite a while. What I'm going to do, let me go into options, and what I'm going to do is look at options. Was it under, yeah, here we go, under formulas. Older versions of Excel might be under calculation. But iteration, I'm going to bump this up. Let's see, maximum, enable iterative calculation. So I'll bump it up to 5,000, and I'm going to reduce the minimum. So minimum change, I'll put it there. Now let's see what that does. Okay, so there you can see now it's marching. Okay, now that's only so interesting again. You know what I'm going to do? I'm going to bump up the surface heat flux. Let's make that 1,000. And so that's moving the temperature up. Well, that's going. What I'm going to do, let's bump the convective heat transfer coefficient back up to 100. And were there any other places where we had convective heat transfer? Not insulated, not there. Constant heat flux, no. Okay, I think that was the only one. We'll go back up. I hit F9. Alright, so that seems to be convergence. Now what I'm going to do, let's select our data, insert, we'll do a contour. That is what it is showing us. Now if you recall from before, one of the things about Excel is it flips this around. So I got to go layout, axis, depth, and then show reverse. And so that is more like what we're simulating. And so this surface over here is our insulated boundary. This is the constant heat flux, and you can see that that has the highest temperature. We have convective and convective here. The lowest temperature is in this upper corner, which is where we have the largest amount of convective heat transfer. So that is an example of using the Excel spreadsheet to solve the heat diffusion equation where you have more complex boundary conditions. And it also shows that you can really play around with this quite a bit. And watch if I change this to 50. Now we'll run that. And so what it's doing is going through trying to converge. And automatically our plot updates. So it shows the utility of this because pretty much everybody has Excel in their office computer, or if you're a student. And it's pretty easy to use this. You can share it. You can do quick kind of back of the envelope calculations using finite difference, and you don't need to have very expensive commercial software in order to do it. The interface is not the greatest. That's because I developed it, but it works. It's functional. And it was originally based off of an Excel code that was in the back of a textbook by Holman, a McGraw-Hill textbook. And that's where this idea, originally the motivation came from, but then I added a lot more boundary conditions, made it a little bit more user-friendly, I guess you could say. So that is the Excel model. In the next segment, we'll play around with radiation and see what that does.